Hi, I'm Ben-Yaakov. This presentation is entitled Miller Capacitance and Bandwidth. So what is Miller capacitance? If we have an amplifier, which is an inverting amplifier, and then we have a capacitor between the input and the output, then the Miller capacitance effect means that we are going to see at the input an equivalent capacitance which is larger the physical capacitor that we have put between the input and output. Well, the reason for that is that when you have such a connection, the voltage across this capacitor is now larger. We have on this side V in, on this side minus A V in, so this is the total, and therefore the voltage is much higher than the voltage that would have been if the capacitor was just connected at the input. And consequently, the current that is needed is proportionally larger. So we can say that the capacitance seen here is larger by 1 plus A. Well, similar effect is happening at the output. The capacitance that the amplifier sees is not the actual capacitor, but a modified value. And in this case, I can get the value by multiplying here by the gain and then dividing here by the gain. So what we see here that with the voltage of AV in, which is the voltage here, we have a capacitance which is C times 1 plus 1 over A. Now obviously if A, the gain is large, then it becomes the same value as the original capacitance. And this can be explained very simply by the fact that if the gain is high and you have a certain voltage here, the voltage here is small. So basically the capacitor is exposed to the full voltage and the correction here is small. Now the Miller capacitance effect could be harmful and it could be useful. It is harmful if we consider, for example, a BJT transistor amplifier, and then we have an internal capacitance between the base and collector. And due to the Miller effect, we see here a larger capacitance, depending on the gain, of course. And consequently, we are limiting the bandwidth. It's a low-pass filter, and the breakpoint will be now at a lower frequency because the capacitance is much higher. So this is actually limiting the bandwidth of amplifier. On the other hand, in some cases, we can use this effect to our advantage. For example, if I want to have a low-pass filter, and for some reason, and there are reasons that we'll see later on, I want to use a small size capacitor, that is a small capacitance capacitor, then I can use this Miller effect to boost the capacitance, and by that getting a low frequency breakpoint as I would have gotten with the original capacitor. Now this idea has been used for many years now in the design of operational amplifier. Here I'm showing this LM324, which is a very old amplifier, and we see here this capacitor. This is a buffer, just a emitter follower with two transistors, and then this is the actual amplifier. Then we have between the output and the input this capacitance. Now it is fed by this differential amplifier at the collector, so the impedance is high. So by this we are generating a low pass filter, or you might say a pole at low frequency, so-called the dominant pole, which helps to stabilize the amplifier for any given load. So this has been used beneficially using this Miller effect. Now let's have a look now at this circuit, which was suggested as means for teaching the effect of a bypass capacitor in this amplifier. We have here a resistor, and this is a bypass capacitor. This is a variable resistor, and the idea is that by moving this slider here, changing the resistance, I can see what is the effect of this bypass capacitor. But let's have a look here. We see here this something that looks like this the Miller capacitor. But in this case, the voltage source is connected to the base via this decoupling capacitor of 100 microfarad. So for all practical consideration, this is like a short for AC. So no question that this voltage source sees now a capacitance which is different from the capacitance of this physical capacitor that has been put here at 1 amperage. But there is no resistor here, so there is no pole here. So this is just loading the input, having no effect on the bandwidth on this side. There is some effect, and here I'm showing the small signal equivalent circuit of this amplifier. There is some effect because at the output we see also this capacitor. Okay, so this is now the capacitance at the output. At the input doesn't make any difference because this is a voltage source which has a very low AC resistance like ground. But at the output, we see the capacitor. If the gain is high, we see the capacitor at its actual value. Now, the resistance is the two resistors here in parallel. So if I calculate the breakpoint here, the high frequency breakpoint, I find that this is 320 kilohertz. Well, it's a very high frequency. But the point is that there is no need to put this capacitor here. Now, if indeed there is a need for this breakpoint, then this capacitor could have been put here. It will be the same thing. And then we would not load the input because I don't know what is this input. And therefore, this capacitor, although it looks like a Miller capacitor, is really not functioning as a Miller capacitor in the full-fledged meaning of the concept. So this brings me to the end of this very, very short presentation. I thank you very much for your attention. I hope you found it of interest. Thank you very much.